Hello and welcome back to Copying Madness. Oh no, D3D12Ez was it called. Ludwig Fusel here, back again with another video on D3D12. I hope you did take the last video right, because it was long and complicated, but I hope it was understandable. Basically what we have done, we have copied Hello World to the GPU. And yes, the video was way too long to do it. What we want to do in today's video is actually talk about the input assembler. So last video we wanted to use the input assembler and we failed because we didn't have memory available on the GPU. However, now we have. Now we have a way to put vertex data on the GPU. In our case, our vertex data is currently Hello World, which is of course not a good vertex, right? And that's what we want to change today. Today we want to make that vertex meaningful, and we want to actually configure the input assembler so that it actually knows how to use our memory that we have created and abused here. Alright, so let's get started. Let's first quickly talk about the input assembler again. Now the purpose of the input assembler on the GPU is to take data from memory, our vertex buffer, to take the data from there and assemble it into actual vertices that can be passed down the pipeline. So in general, it is kind of like a access proxy to the GPU memory, you could call it, right? The pipeline, the vertex shader, is never gonna access the memory. The pipeline is never gonna be accessing the memory. The input assembler. The input assembler is gonna access the memory. It's going to lay it out in the correct way, and it's going to pass it down to the subsequent stages of the pipeline with associations like what is a triangle. This is the concept, and today we're going to talk about how that works. Now, in general, the input assembler does that. How do we need to configure it, and what are kind of like the nuances to configure the input assembler? Well, in general, on DirectX 12, there are two sides to everything. There is the static configuration of the pipeline. The static configuration is a configuration that you create once and reuse multiple times. The static configuration contains data like the actual programs that execute, like the shaders, the layout of your vertices, the configuration of the blending. All of that stuff is kind of like the static data or the so-called pipeline state. This pipeline state has a configuration part for each part of the rendering pipeline, and that needs to be configured correctly. And then what you're going to do at runtime is you're going to bind the pipeline state to your command list, to your kind of like GPU path that you want to do. And then you need to fill the pipeline with live by basically associating data with it. So the input assembler basically works by describing in the pipeline state how the layout of your vertices is. And then at runtime, if you are executing the pipeline state, you basically tell it, all right, you know how the data shall be laid out. Okay, I tell you, there is the data located. This is how I currently want to use it. This is done dynamically. So you're always going to have two sides to it, a static and a dynamic side. Let's get started by defining the static side. Now, in general, these were our resources that we created. Now down here, actually, before I'm going to do my copying, actually, I want to keep it together. No, let's keep it together, even though this is not how you would do it in a production-ready environment. Let's keep it all separated and simple. Let's maybe mark them, right? These are kind of like common stuff. This is kind of like upload, and vertex buffer. And let's now define my own section and call that one pipeline state. Now the pipeline state is the first thing that we want to configure. How do we configure or create a pipeline state? Well, in general, there's a function on the device that creates myself a pipeline state. Create pipeline state. That's a function. The function is actually quite simple. We need a descriptor and IID PPV args, and it's going to create myself a pipeline state. We're not going to call that one for quite a while. We're not going to call it until we are completely finished. If we have done and configured every part of our rendering pipeline, then it's going to be time to call that function. We can't do it before, because before it's always going to fail and our application will crash and we cannot validate that at least the calls work and our application still runs as expected. So the only thing that we're going to do is we're going to define the descriptor, even though we are not going to use it. It's graphics pipeline state description. This is the one that we are calling here, GFX PSO disk. Or let's call it PSOD. This is kind of like the structure that we care about and that we want to fill. Now, in our case, we just need to fill it for the input assembler. Just that you are getting a hint on what this is. This is a big boy. If you take a look at this, this is the structure that we need to fill over the next 5 to 10 videos. Probably more 10 than 5. This is the structure that we need to fill. How do we fill it? Well, each part of that structure is associated to a certain primitive of the pipeline. Now, these are all shaders, root signature and stuff. We don't care about that yet. Blend state, we don't care about that. Stream output, we don't care about that. Rasterizer, we don't care about that. Depth stenciling, we don't care about it. Aha! Input layout, index buffer, stripe cut. These are the two boys that we are talking about, or girls. I don't know. I shouldn't talk about that. I want to get forward. Everything else here is something that's related to different part of the pipeline. These two are the only ones that are relevant for the input assembler. And it seems overwhelming, I know. But these two are important. Index buffer stripe cut values. Disabled. This is a special thing called indexing. We are not going to talk about indexing now. We're going to talk about indexing in like later videos on like how rendering works and how we can optimize stuff. Basically, indexing allows you to reduce memory usage, and vertex or line stripes allow you to reduce memory even more in the indices. And if you are using stripes and indexings, then you need to specify this one correctly so that it works. It's a really, really rare edge case. 99% disabled. So I'm not going to talk about that into too much detail. General concept is reuse of vertices by not using the vertex data in general, but indexing into the vertex array. And stripes are basically the idea of taking 3 vertices for a triangle, then discarding the first one, taking the next one too, and building another triangle out of these, discarding another one, taking another one to there, and reusing it again. These two methods, you don't need to really understand them, how they work, combined together, require that value to be set. However, we don't care about these. We care about our input layout. And now you would think, all right, input layout, it's a simple value. Wrong. And this is like the beauty of that one. The most members of the descriptor are actually structs themselves. The input layout, if I would peek into that again and peek further, you can actually see is another struct. Now it's a simple struct, just 2 elements, and you're gonna be lucky. This is one of the simple ones. There are more complex ones. There's one struct that contains like an array out of 8 other structs that itself contains structs and enums and stuff and madness. But this one is simple. We just have number of elements and elements. The elements that we need to define are input elements in an array, the so-called input element description. It's a simple one. It is kind of like the layout of the vertex, which we want to define here. Now currently, let's maybe move that down here. This is kind of like the vertex data. It is now here, vertex data. And this is kind of like later on going to be used as the vertex itself. So vertices, this is kind of like what we're going to use as vertices. Now, of course, I need to take over the vertices here. And then what we're going to also define is input element, and we're going to call this vertex layout. And since this needs to be an array, I'm going to do it like that because, well, a vertex layout is always an array. In our case, we're just going to have one entry in there, and we're going to define the vertex layout as a reference. Where is it? Here. Input layout. So number of elements equals count of, we're going to use a macro here, count of vertex layout. And then down here, the description itself as the vertex layout. That's the general usage. That's the most simple usage to use it. It's automatically gonna adapt. Now let's talk about the layout itself. And Visual Studio is sometimes a bit mad. Okay. So let's talk about how an input element is laid out. Well, basically an input element is kind of like one set of data for vertex. For example, a two-dimensional position. A three-dimensional position, just a plain old integer, or a more complex data type. That's the idea of an input element. For example, if you want to define like a 2D renderer, a vertex would have a two-dimensional coordinate as a position, maybe a two-dimensional coordinate as a texture layout, and a 132-bit integer as a kind of like texture index to know which texture to use. Then it would kind of like have 3 of these certain kind of like elements, and you would have like 3 of these input element descriptions that tell the GPU on how to use them. Now, each of these input elements has certain properties. They have a semantic name, index, format, input slot, byte offset, input slot class, and instance data step rate. Now, let's walk through them step by step. Maybe let's put the header here to the side so that we can reference this a bit better. Now, the first one that we need to specify is the semantic name. This is just a plain old string. This string can be anything you like. Later on in the shader, in the code that runs on the GPU, you need to reference the actual data. So later on in the shader, you're going to have a struct or kind of like an association of the input vertex data. And so that the shader can be linked to the actual vertex data, you need to give it a name. The semantic name is being described in the shader, and it's being described in here in the input layout, and these two are matched so that we can access the right data from the shader. In this case, it's a position. As simple as that. We're going to just define a two-dimensional vertex and a two-dimensional triangle, so position. It's going to be as simple as that. The next thing is an index. You can have like multiple positions, or several semantics can have multiple positions. Since we're just going to have one, the index is 0. The next thing is the format. The format is kind of like indicating how big or what kind of data is in here, which is going to be the DXGI format, R8, or no, actually not R8, because we're going to use floats, and floats are 32 bits, so R32, G32, underscore float. This is the type. This basically means 2-channel 32-bit floats, which means 2 floats, or a float 2 on the GPU. 2 floating point values, 1 for X, 1 for Y. Since it's DXGI format, and DXGI format is kind of like abused here, it needs always to be RG. I don't know, maybe they have aliases for X and Y already, I don't know. No, they don't. So just R and G. Don't let you fool that these are colors. They can be everything. In this case, R and G, 32-bit floats, as simple as that. The next thing that you need to specify is the so-called input slot. The input slot specifies from which vertex buffer view that we're going to specify later it shall be used. You can bind multiple vertex buffers. And this is kind of like indicating from which vertex buffer you want to take the data. For example, you could have one vertex buffer for the positions and one vertex buffer for texture coordinates, for example. Doesn't make sense in such simple scenarios, so the slot is going to be 0. It's going to be the first and only one. The next one is the input classification. The input classification indicates how the semantic shall be interpreted. So D3D12 input classification here, you can have per vertex data and per instance data. In DirectX 12, there's a concept of index rendering, which basically means take the same vertex data but render it multiple times. And this allows you to either use this input slot to increment on a per vertex base or on a per instance base. Most of the time, per vertex data. This data is on a per vertex base. It's going to increment to the next element on every new vertex. Now the next thing that we need to specify is the instance data step rate. Since this is a per vertex data, this is going to be set to 0. If you're using indexing, it's gonna increment on a per instance base. Now I see that I'm an idiot. I forgot after the input slot to define the aligned byte offset. This is actually the offset within a vertex. So a vertex is a certain size, and this is kind of like the offset in the vertex. Now in general, you might want to align data. In our case, it's the first element, so it's also going to be set to 0. Now this is also why my autocomplete didn't work. All right, can close that. Very simple. First one, a name. Then, of course, I now forgot the layout again. Sorry. First one, name. Second one, index into that naming convention. Same name, multiple times. You need the index. Then the format, what is kind of like the format of the data. In this case, it's 2, 32-bit floating point values. Input slot, which vertex buffer to use. We just have 1. So the first one, index 0. Then the offset, it's the first element. So we kind of like put it to 0. Then we have the input classification. This is data that changes on a per vertex base. So we put it to 0. Since we are not using instancing, 0. And that's basically the idea. You have one row for each of the data. You could also do it differently, right? You could also define it like that, like position X and position Y, and you could specify it both times as that one. The only thing that then would need to change is kind of like this offset, right? This offset would be now like at 4, because now we have kind of like a 4-byte offset, a 32-bit float offset in between here. There's, I think, also a macro for simplifying that. I hate it. If I would peek that quickly, it is called aligned byte offset. There's a macro like D3D12 align. Append, that one. Append aligned element. This is basically, I think, -1, where everything at 0xff. This is automatically gonna take a look on how big was my element before that. All right, this is 4 bytes big, so the offset is gonna be 4. And if I would do another one like Z, all right, I am already at offset 4, and the other one is also 4 bytes big. All right, now my offset is 8. That is kind of like the idea here. It simplifies the usage to these. But that's not what we want to use. We want to use the most simplest one, RG. 2-dimensional position. And that's everything that we need for our vertex layout. Now, the only thing that we now need to adapt to that is the actual vertex data. Now, the first thing that I want to do is I want to define myself a vertex. So let's define myself a struct vertex. And then instead of having the vertices as a hello world, let's actually define the vertices as an array of vertex. The vertices is an array of vertices, of course, but you get the point, right? And since we're going to have 3 of them, I'm going to do it like that. Now, what are going to be the parameters? Well, we have 2 floats, X and Y. As simple as that. Right? We defined that we have position, 2 floats, so our vertex are 2 floats. If you would have another one, like texture coordinates that are always indicated as your V, and we would have something like that, then we also would make it like that, right? The layout on the GPU might be a different one. Or we could also have like a padding here, P0 and P1 as a padding. Then we could have like a different offset here. So like 4, 8, 16. Right? This is something that could work. Now, the paddings are not usable, but they are on our CPU side. And that's something that you just need to get a bit of used to. You need to model these data, how they fit you, how they fit your application. You need to think about like stuff like padding, which might be optimized. You might want to pack them together, like U and V, and don't use padding here and directly offset it. That all depends like on your application and measurements and what performs best on the GPU vendor that's sponsoring like your development, right? There are like games that are especially developed for NVIDIA GPUs. They kind of like follow NVIDIA's best practices and like stuff like that. That's basically the idea. But in this case, keep it simple for now. X and Y, no advanced stuff, just a position. Now, let's put in some data in here. We want to draw a triangle. So we need 3 vertices. How are the vertices laid out? Well, it's a triangle. I want to have a normal triangle. So bottom left, center top, bottom right. Well, that's exactly how we specify them. Normalized device coordinates from -1, -1 to 1, 1. Of the extents of the screen. We start at the bottom left, which is -1, -1, all coordinates to -1. So let's specify them like that. Let's maybe duplicate them like here and then adapt them. Now the one at the center top, x coordinate 0, y coordinate 1 means 0 center, 1 top. All good. Now bottom right, x coordinate of 1 to the right, -1 to the bottom. Quick and dirty, quick and simple. Nothing special on it. As simple as that. And we have vertices defined, we have an input layout defined, and we have bound that correctly to the pipeline state that has not been created yet. Only thing that we need to change is that one here. Simple size of vertices. And now we also have them correctly copied. Now the only thing that's missing is the dynamic binding. How does dynamic binding work? Well, it's actually not too hard. What we need to do is we need to bind the input assembler. So EA, input assembler, that needs to be bind on the comment list. Now, everything that has something to do with the input assembler starts with the IA prefix. Now, what functions do we have? Set index buffer, set vertex buffer, and set primitive topology. I told you that we're not gonna talk about vertex or index buffers yet. We're gonna probably talk about index buffers in a future video, but for now we don't. Now we don't use index buffers, so we only gonna set the vertex buffers. How do we set a vertex buffer? Well, we have a start slot and the number of vertex buffers that we're gonna set. Well, start slot is 0. This is exactly like the slot that we specified up here in our layout. In our layout, we specified slot 0. So if we specify slot 0, we also need to bind to slot 0. We could also define slot 1 and bind to slot 1. Would be no issue. And then what we need to do is we specify the number of vertex buffers that we want to bind. I told you there are multiple possible. We just want to bind one. And then what we have the vertex buffer view. Now, what is the vertex buffer view? Well, the vertex buffer view is a structure on the GPU, on the CPU side that is it is a view, but not a view that needs to be copied to the GPU. It's just a view that's bound to the comment list. It's also simple to define. Vertex buffer view, VBV, as simple as that, and bound in here like that. Now the VBV of course needs to get some parameters. It's actually not simple. We first have a buffer location, so what is the buffer that we want to use? Now the buffer location is a GPU address, so we can't like plug in the vertex buffer. This doesn't work. I mean, it does work, but it doesn't work, right? We actually need to call it and we need to get the GPU virtual address. It syntactically works because both of them are kind of like pointers or uints, but you need to call the function get the GPU virtual address. This kind of like gives you the address of the vertex buffer and it binds it in here. Now additionally, you can or you need to specify the size and the stride. The size of the vertex buffer, well, size of vertices. It's quite simple. Next thing that we need to specify is the stride. So how big is one vertex? Size of vertex. As simple as that. We could even make this a bit more consistent by specifying it like that. Count of vertices times size of vertex. It also kind of like makes sense. So maybe we're going to keep it like that. Now, as you can see, the data is never going to change. So actually, we want to factor that one out down here somewhere. Here, where is my pipeline state here, but we want to factor it out to vertex data actually, but we can't. So let's maybe put it in here. Vertex buffer view. We just need to describe it once at application start, and we'll rebind it every time we run. Next thing that we need to bind is another AI. We need to define our primitive topology, because for now we have just defined the vertex buffer and we just told how a vertex is laid out. But what the GPU and the input assembler is still not knowing, it's not knowing what type of primitives we are processing, right? We could process points. We'll just take like each vertex and we would have 3 points at our screen. We could also process lines. So we have 1.5 line on our screen. Or we could process triangles and we would have 1 triangle in here, which is exactly what we want. D3D12 primitive topology. D3D12 primitive topology type. And we have undefined, point, triangle, and patch. Patch is used for like the tessellator. We don't need that. We use triangle, which we can't. Why can't we? here set because it is it's actually, I think, just D3D. No, what is going on? I hate it. D3D12 primitive topology. Yeah, I think it's that single one. Is it just primitive topology and what? Okay. I made a mistake. It's just a primitive topology, not a primitive topology type. This is actually even more finer. You can actually have a list of lines, a line strip, a point list, a triangle strip, right? There are like many primitives in here. What we are talking is the so-called triangle list. So it's a list of triangles and it's D3D12 primitive topology, if this is even defined, because actually it is not. This is actually just defined as D3D12. Or just D3D primitive topology, and we want to have a triangle list. This is why it always is a bit confusing with D3D12 and just D3D. I don't know why, but these qualities don't change between DirectX 12 versions, so it's D3D primitive topology triangle list. It's an advanced parameter, and you can kind of like optimize that by strips, and I told you that if you are using strips and if you are using indexing, there are special things that you need to take into account. In our case, it is a list of triangles, right? This is a list of triangles. It is a list of one triangle, like T1, triangle 1. One triangle interpreted as is. If we would have another triangle, we would need to define it like that as T2. That's how it works, right? As simple as that. That means triangle list without indexing. Right. So this is basically how we bind that, and that is input assembler done. And now we can draw. Finally, we can call a draw command. It doesn't make sense, but we're going to call it draw instanced. That's the call that we want to do. We need to specify a vertex count per in the instance, count of vertices. This is how many vertices we want to draw. Instances, one instance, start vertex location, 0, start instance location, 0. We want to start at the first one. That is how simple rendering works. Draw instance, done, finished, F5. And we're gonna see nothing. Of course, we are on release. That's not a good idea because we want to see if we made something wrong, which we actually did. I'm going to show you what we did wrong. We have a bit of problem with memory management currently, the way our application is structured. I'm going to show this to you in a second here. So our application is running. I can press Alt F4. You can see that we have many things. Actually, we do not have live device objects. Yeah, because our device is correctly cleaned up. However, actually, it's not done in the right order. That shutdown call here is actually not the last instance of the device that's that shut down. The debug layer shutting down here. This is why we don't get any issues because our resources are at the end cleaned up. However, we want to close our resources here. So our vertex buffer needs to be released here. And our upload buffer. Now the order is again in order. That's kind of like the idea. It doesn't give us any issues. The only issue that we do get here is that no pipeline state has been set on the comment list. The general idea is we can't render until no pipeline state is set, or we can render. However, we're going to use the default no pipeline state, and no op means do nothing. Of course, no op, no operation. Pipeline state, we can't do it because we can't create the pipeline state because it's not filled out correctly. We need to deal with everything, really everything that we have dealt with. We need to deal with everything. And only if we have taken a look at all states of our rendering pipeline, we are ready to render. And maybe it's going to even happen earlier than you think, because I think we are not even that far away. Maybe 3 videos, maybe even just 2. Maybe I also was talking and scaring you away without any proper state because I made a logical thinking error actually. I thought that we really need to configure every part of the pipeline, but we're not going to use every part of the pipeline, so we don't need a dedicated video for every part of the pipeline, right? So we're probably going to configure everything that we use, and then we're going to skip directly to the end. That's the end of the story and the end of the video, actually. Thank you for watching. Sorry for that. Make sure to like and subscribe, and see you in the next video. Have a nice day. Bye.